Now let's talk about what to do if you have two samples and would like to compare the in parametric approach we compare the average of the samples, which average is larger or the average is the same. In the parametric solution for this case, it's a two-sample t-test for mean values. Again, we cannot use mean values in this case because the data is not the data is problematic. So we will use the median values again. Okay, and then the test is called Wilcoxon rank sum test. You see, the name is quite similar to what we had before. Before it was Wilcoxon signet rank test. Here we have Wilcoxon rank sum test. And sometimes it's also called Mann-Whitney test, and I think it's easier to call it Mann-Whitney test just to avoid any confusion. Okay, and the test also is based on the ranks. Let's discuss it. So we have two samples taken from two populations. We would like to know if the median values for the populations are the same or not. Okay, so that's the procedure. First of all, we need to rank all values in increasing order of magnitude. And we don't take into account groups, so we just treat all values as taken from the same sample. Okay, so the rank number 1 will be in the for the smallest value, rank number 2 for the next smallest, and so on. So that's the first procedure. The second procedure is following. Let's say we take sample 1 and sample 2. Okay, so we take all values from sample 2. Let's take the first one. Take the first value from sample 2 and count how many values in sample 1 are smaller in ranks. Okay, so how many values have smaller rank, and then sum up all these values and get the statistics, and then use the statistics to calculate the p-value. Again, maybe it sounds a little bit confusing. I'm going to show you an example. So that's again, we use Varda and Riva, and in this case we are going to compare the median. Can we say that actually Varda and Riva are equally contaminated if we are talking about the median contamination? Okay. So that's the first procedure. We need to rank all values in increasing order of magnitude, regardless groups. And that's the results. Okay, so you can see that if you look at all values, the smallest value is 124.8, right? And that's the rank 1. Then the next smallest is 129.1, and that's the rank 2. And then you continue, and you don't take into account the group split. You just treat it as just one big sequence of values. So that's a relatively easy step. Now the next one is the following. It's just a sum of ranks. Take the sample with the smallest sum of ranks. It will simplify the procedure. So we will take the basic sample will be Riba because it has the smallest sum of all ranks. Now look what we need to do. We need to take this procedure. Okay, we need to take every value from this basic sample and find how many values in the second sample have rank smaller than this one. Okay, let's do it. These are already the values. I will show you the procedure. Okay, let's take the first value. And the first value in this sample, in the basic sample, is 17, right? So the rank is 17. Now let's count how many values have rank below 17. So let's see. 1, 2, 3, 4, 5. This one is above. 6, 7, and then 2 above, right? So we have 7 values in Varda with rank larger than the first value in Riba. Okay, so that's 7. That's 7. Okay. Now the next value has rank 9. How many values in the second sample have rank smaller than 9? Okay, let's count them. So 20 is larger, 19 is larger, 11 is larger, 10 is larger. So we have only one value, it's this one, right? So only 5 is smaller than 9. So we make it 1. Then the next one is 8. Again, we count how many values. It's the same 5, so it will be 1. Then we have 0 here, we have 0 here, we have 1 here, and then we just continue. We have one relatively large rank here, so therefore it will be, in this case, it will be 6. Okay, so that's it. Now we just count, sum all the values here, and that will be our 17, and that's our statistics. So U equal to 17. So that's our statistics. Again, we need to know how this statistics is distributed in order to make a test. And in this case, like in the previous case, the statistics is, follows normal distribution. Again, if number of values is equal or above 20, that's the average and standard deviation for this distribution. Okay. So it means that if null hypothesis is true, this U value should be very close to this one. Okay, it can go a little bit above, a little bit below. How far it can go? It depends, of course, on the standard deviation. Okay, so we can calculate the Z value, meaning how far the U statistics is distanced from the average value in standard deviations, and then we can use the normal distribution in order to find the p-value. And if we do this procedure, the average will be 50 because we have n1 and n2 are 10, so 10 times 10 and divided to 2 it's 50. Then if you calculate standard deviation is 13.23. So that's the, and you can see this is 50, this is 17. 17 is pretty far from 50, right? So you can see that the standard deviation is 13.23, so double standard deviation will be 26, right? Two standard deviations from 50, it will be 24. But we have 17, so it's even smaller than two standard deviations. So if you calculate the z-value, you can see it's minus 2.49, which for the normal distribution is of course quite extreme. And then if you calculate the p-value, you will get 0.013, which is 1.3% chance to get a sample like we have, even with this statistic 17 instead of 50, or even more extreme. So in this case, it means even more distanced from 50. And then only 1% chance to get a sample like we have, or even more extreme if null hypothesis is correct, if median chloride content in this rivers is the same. So we will probably reject null hypothesis in this case. And again, if you compare it with the t-test gives you a p-value 0.08, which is smaller. So it means that in this case, the Mann-Whitney test also has a smaller power. So if you have an effect, if you have a small effect, the chance that you will see this effect with this Mann-Whitney test is smaller than the chance to see this effect with the t-test. But on the other hand, if your data is not very good, that's the only possibility you can use. Again, that's how to make the test. Again, use exact equal to false only if your sample size is small. In our case, of course, Ribe and Wader are small sample sizes for the non-parametric test. I use them just because it's much simpler to use 10 and 10 values instead of 20 and 20. But in reality, you should have at least 20 values in one sample. And then you can see that the procedure is very simple to the t-test. For two samples, you just provide two vectors with the real values, and then the function Wilcox test does everything for you. And again, if you want to use only one tail, then you can just provide this parameter alternative.